we got 15 people, including us, so I suppose we can start. So today I'm very pleased to welcome George Hagerman from Old Dominion University to talk to us in our MIE department seminars. And as George mentioned, we have recently been collaborating and communicating in regards to the Ocean Energy Safety Institute, which is relevant to oil and gas, offshore wind, and marine energy installations around the country. And so that's, so I've been so fascinated with some of what George has been mentioning during those meetings that I was so inclined to invite him to talk to us about his interests. George is connected with the Coastal Physical Oceanography Center with ODU. And before that, you were with the Virginia Tech, right? And coincidentally, I was at Virginia Tech last week, and they gave a talk at their department seminar series on actually on mooring systems for offshore wind turbine.
Oh, awesome.
So I'm sure they have a recording of it, which I think I'll pass on to you.
That'd be great. We were actually, we're actually. Well, anyway, I don't want to divert from my own talk, but there's definitely, there's definitely interest in doing some subscale floating testing right. Actually in Virginia, even though we don't have a floating offshore wind resource per se.
But one thing which is very, very interesting to me is George has been very involved with the offshore wind developments off of Virginia. And from what I understood, talking to Walt Musial at NREL, is you have been involved with looking at some of the instrumentation on these platforms and looking at the data that comes from the real site. I mean, this is not simulation data. It's not experimental data. This is actually a real thing from the ocean and from a real platform. So I'm very curious to hear what George has to talk about from his experience working with the Virginia offshore wind. So let's give George a nice welcome. Over to you, George.
Thank you so much, Krish. And let me just say to your point, I am not, that's one of the things, and I want to give a shout out to my colleague at Tufts University, Eric Hines, who has been doing a really amazing job along with the University of Rhode Island in instrumenting the Block Island, one of the jackets there. And we are hoping to replicate that. And I don't want to say any more. I'll leave that up to Eric maybe during the discussion period. But we are hoping to replicate that at the Seabed pilot turbines, because these are monopiles. These are the first monopiles, just like Block Island is the first jackets. And of course, jackets and monopiles respond very differently to wave loading. And in particular, they respond very differently to breaking waves. And so that'll kind of segue into my talk.
Yeah, nice.
So let me just go ahead and again, thanks for this opportunity. Let me just go ahead and now start advancing my slides. So these are the topics I'm going to talk about. I have 6 topics. Some have more slides than others. And the way I'd like to do this is as I go through each topic, if there's something I present that is not clear, or you would like me to go back to a slide, that would be the opportunity, and then I'll go on to the next topic. And then for sort of general discussion or what's next, or that kind of thing, where I hope Eric and Lou and Spencer and others who I recognize just from the literature and from their interest in this topic, that will do that at the end. And I'm hoping there'll be about 20 minutes remaining for that kind of discussion. I've got about 30 minutes of talking, and I don't think clarification should take more than 10 minutes unless I've done a really bad job with my slides. So let's go ahead and then get started to the first topic, which is the breaking wave criterion that's in the standard. So this will be available. The PDF of this will be available along with the recording. So I'm not going to go through this except to say that in the extreme sea state model, which then is used to drive several of the design load cases, the important number on this page is the 50-year return period. You will see off Virginia, Hurricane Isabel looks to be about a 30-year return storm. So it is not the most extreme event that we've seen. I mean, it doesn't represent the 50-year design event, and certainly not the 500-year robustness check, but it does represent a pretty intense hurricane. It was a Cat 2 when it made landfall. So that's the only thing here to really take away is 50 years. And then and of course if you go through this, you'll also see that in terms of the design, it refers to Annex B. And so I'm now going to present Annex B. That's where you really, okay, are my waves breaking or are they not breaking? And it turns out despite the sophistication that is in the wave height distribution formulas presented in Annex B, the breaking wave determination is very simple. It's the Mitch criterion, which is H over D. So when the individual wave height, after you do your you do your probability distribution of individual wave heights within the sea state, the 50-year design sea state, you then check to see if the maximum wave or the most probable maximum wave, and there are a variety of ways that that's defined. But if that wave height is equal to or greater than 0.78 times the still water depth, which of course you have to factor in storm surge and the worst possible combination of all that. But it's very simple. That's a very simple criterion, and it's not terribly sophisticated. And I guess I'm going to steal my punchline, which is I believe that this is overstated by a factor of 2. That as it says in the abstract, that you should suspect depth limited breaking when the significant wave height is only is 1/3 of the local water depth, and in fact that individual wave height that breaks is half that value, the ratio that, and we'll see that, and this really comes, it'll be my last slide, and shout out to Spencer Hollowell, who's on here, who's the lead author on the very last slide I'll show, and it's really the take-home slide. It's the slide that really cements all this together. And let me proceed. So this is it's a very simple criterion. I don't think sufficient for what we're doing. And okay, so let's take a look at sort of what we know about hurricane wind and wave fields. So this is just sort of a diagram of what you see, and this is not something they see in the extratropical design world of the North Sea. So you don't see these long forerunner swell, which are indicated by the red dashed lines that are generated, and they typically propagate along track. And this is kind of a conceptual diagram that I first presented at Power US back in 2017 when Hurricane Jose was quite recent. And so it sort of shows that you've got these forerunner swell, and then as the hurricane wind field arrives, it generates a short crested sea, shorter period wind waves that literally in the front forward portion of the storm, particularly the front left quadrant, will literally cross the long period swell spectrum. And so really creates the opportunity for very typically steeper waves and certainly more opportunity for plunging breakers. This actually sort of shows that where you've got, this was a forecast. I took a snapshot of this during the forecast for the arrival of, this is Wave Watch 3 that was running at the time, the operational model. And so you see the very narrow spread, the purple with the very long period high peak that's traveling north, almost due north, maybe north, slightly west of north. And then you see the very broadly spread shorter period peak wind sea spectrum crossing that swell. So it creates a very chaotic sea state that I don't think have adequately studied in my very limited. I mean, I don't do this every day. I do a lot of other things in offshore wind. So again, if anyone in the audience knows better or more, by all means, I want to hear about it at the discussion or by email after this. And of course, the short period, again, you can see the short period is kind of lagging the wind. It does start to rotate, but the wind actually, as the hurricane progresses, the wind field actually, which you would expect, the winds will actually veer, in this case, counterclockwise, and it takes a while for the short crested sea direction to catch up with that. So this is all very consistent with our understanding of the wind and wave fields. What's been measured? So now those are just a sort of a diagram. So this is Hurricane Isabel. It toppled over one of the wave riders. You can see we've got a really a very strong record of the wind speed and good wave measurements. And we'll see later a SWAN model that actually looked at how was the energy dissipated by Isabel as it crossed the shelf. And again, I'm synthesizing a lot of different studies here, but they all point to the same thing, that surf zone breaking or depth limited breaking is occurring on our shelf in water depths where our wind farms will be located. All right, so this sort of shows the maximum. This is if you want to mine this for more information. So I don't really want to dwell on that, just to say we really have a good understanding of this particular hurricane and can have good validation of models. More about Isabel. You'll see later, it's the strongest hurricane we've experienced in the offshore wind region. All right, so this is another one. This is an earlier modeling study. And it just sort of shows the same idea that the hurricane approaches the coast. This is Bonnie. And you can sort of see the idea that it's generating swell. These are wind speed contours. But you can sort of see there are these contours that are right along track, and that swell. And then as the hurricane approaches, I mean, this pattern goes over and over with tropical systems. I'm just showing some of the strongest hurricanes and what's been published in the literature about them. So again, you can see the wind field and you can see the wave field, and you've got the winds crossing the waves. I mean, so this is a concern when you start to, one of the things that's, again, not been widely thought about, but it was certainly saw it early on in some of the literature, is there's a lot of aerodynamic damping that can take place, not in obviously the rotor's parked and in survival mode and the blades are fully feathered during a storm like this. But in other tropical systems, and we'll see an example of this with Hurricane Irene in which I'll show at the very end of this topic, you'll see that you could be having the wind turbine actually operating, but the waves are actually edge on, are not. There's no aerodynamic damping of the motion of the turbine because of the edge on approach of the short crested waves. This is Irene. So again, these are the kind of the wind swaths in meters per second. This is at U10. So this is not at hub height. This is at 10 meters above sea level. But this is really worth looking at. So you can sort of see, these were some snapshots I took during the hurricane when they were available, or a couple of days afterwards. And you can see that the wind speed, and this has all been adjusted for hub height, so that the turbines at this location, which is buoy 44014, which is actually near the edge of the shelf, but it sort of shows it would be operating because it was the mean wind was below the cutout speed of 25 meters a second. And you can see that the wind direction of the wave, there's quite a bit of variability, almost 90 degrees, not quite, but the wind direction is coming from 90 degrees, and the waves are coming from east of south, which is again what you would expect for the track of Irene as she came up from the southeast. So this is all very consistent with what we know how tropical storms make landfall throughout the mid-Atlantic bight. These are just a couple of examples where I've got more information. All right, before we go on to this, any question about sort of the nature of the wind and wave field? I went through a lot of stuff pretty quickly there. You can go back at your leisure and look at these individual storms. Any questions about that?
No, this is, George, this is great. Very interesting. Now, can you talk about bidirectionality of the sea states as well?
Yeah, I mean, the bidirectionality is what I shared in the very early part of this, which is this has been the best, and we've now had several storms. I know this from Chris Baxter at URI. There's now an excellent data set that will probably show these kinds of events since that Eric and Chris installed this system on Block Island. So I'll maybe wait until the discussion and Eric can talk about it if he wants to, if the data may not have yet been synthesized and we were just past the hurricane season. But I know just from emails from Chris that they've gotten some really good data during some tropical events this last fall.
Okay. Thank you.
All right. One slide here. This is Jeff Hansen, who is a really world-class wave modeler, was with the Army Corps of Engineers Field Research Facility. He now has his own Wave Force Technologies business. But he really took this thing seriously, and we got a little funding from DM at the time. It was called Virginia Department of Mines, Minerals, and Energy. It's now called Virginia Energy, but at the time he actually did a very thorough bookkeeping of the dissipation source terms, and then I've plotted these at his results at a common scale. And I have to confess, I do not recall what the energy units are on that scale, except the hotter, the redder, there's more energy being dissipated. And you can see that bottom friction dissipates some energy, white capping, which, the white horses we see, the spilling breakers that we all can see in a fresh gale or anything like that in deep water. But this surf breaking is by far and away the major source. And this was assuming an H max to D of 0.73, very similar to the Misch criterion. And again, as we'll see later, that this is probably not conservative enough. But even with this, you can see that I don't know if you can see, and the upper right is an enlargement. This is where the CVAL pilot turbines are. So they're clearly if Isabel had just been shifted, its landfall had been 20 or 30 nautical miles farther north, there would have been a lot of plunging breakers, perhaps in the commercial wind energy area, or farther south, Kitty Hawk. So this is, I think, and this is the only slide I have on this. I'll have to see, to be honest with you. It was sort of gray literature. Jeff never published this, but we can certainly see particularly if we move forward in the Ocean Energy Safety Institute and look at this area. I think it'd really be good to have a workshop on this whole topic, and that's what I'm really trying to stimulate interest in. I think it's maybe a joint industry project. But this is the only slide I have on that before I get to synthetic hurricane model results. But any questions about, and I'll answer them as best I can. I wish Jeff were with me, but I can get him for the workshop. All right. So, and again, these are all very different ways of looking, and yet they're all telling, I think, a common story, or I've tried to synthesize a common story. All right. So now on a completely different note, so hurricanes are sufficiently rare that you really can't use extreme, like we have probably, I would say anywhere from, depending on the season, of course, in the El Nino, La Nina pattern, but we could have anywhere from 10 to 15 more. For every hurricane we might have 10 or 15 extratropical events with the same, extratropical nor'easter, we call nor'easters here off the Carolina Capes and the Virginia Capes. Those, so you don't have a big enough population to really reliably do the extreme tails. So we did a study, and the link's at the end of this slide deck. But Boehm funded a study that included Jeff Hansen when he was at the Field Research Facility, and included Peter Vickery, who developed the synthetic hurricane model, and it's used in the ASCE design standard for coastal buildings. And so this was the first application of this synthetic hurricane model to oceanic regimes. And so let me quickly kind of go through what that looks like. And if there's a whole lot more slides I could present, but it basically is you divide he divided the Atlantic all the way out over to the equatorial Africa, where the waves first come off the northwest coast of Africa. And you basically get a radius to max, you get a distribution of radius to maximum winds, central pressure reduction, heading and speed. And then you create a wind field model. And there's a variety of things that are done. And I don't really want to dwell on that, except that I think it's a well accepted, certainly all the coastal building, I mean, ASCE uses it for their building standard. And BOEM, I know that Dominion ended up using Peter Vickery to actually run specific synthetic hurricane modeling for the 2 sea-valve turbines that are out there now as part of the front-end engineering design study. And I reviewed Peter's work. And in fact, probably the Dominion did that because I tried to say, look, you've got to really do it this way if you really want to know the hurricane situation. So I'm just going to show you some results that we did publish. And again, here's the validation of how do you validate a synthetic hurricane model? Because there's 111,000, almost 112,000 simulated hurricanes, but these are all synthetic. And so Peter took out a weighted subset, a much smaller subset, so that he could actually have a manageable set to do wave hindcasting. But this is still way many more events than are available in the historical record, where we have good wave measurements, where we probably only have, I'd say we probably have less than 50 hurricanes, certainly less than 100, since we were actually measuring waves reliably in the 1960s. And you just can't do a 50-year return period when you've only got such a small population. So anyway, the blue squiggle line shows the weighted subset. And then it's kind of a reality check. He actually ran the synthetic hurricane model for the same parameters, these different parameters, Rmax, central pressure reduction, heading and translation. He ran the same process for actual storms. And this is where they end up. And so, yeah, there's a lot of scatter because these are real storms, and they're not going to always behave like a statistical distribution would predict. But you can see Isabel is one of the strongest storms and has a 30-year. Now, Floyd has it looks like it might have been comparable to a 40-year return period. But, we certainly have.
Excuse me, George.
Yeah.
Just for the benefit of the audience, the general audience, if you can explain what the return period in x-axis means and what the gust wind speed actually means. Thank you.
Yeah. All right. So very good. So that's a good question. So this is the horizontal axis is a log of the return period. So the design standard, the IEC 61400-3 is a 50-year. So you're looking actually for the 50-year return periods, which is, this is 20. I'm looking at my cursor along between 10 and 100. This is 20, 30, 40, 50. This is the 50-year return period. And you've got, we'll just call it very even, a peak gust wind speed of 100 miles per hour. Peter did not use, he used MPH. It's always confounding when you've got to deal with all these mixed units. But anyway, that's what he did for the study. And I guess that's what ASCE also uses. In any case, and then, so you can see, and then if you go to the 500-year robustness check, so 100, 200, 300, 400, 500, you're at the robustness check, you're right at the class 1 upper bound. And I've normalized, you have to be really careful where the gust, different gusts have different time periods. There's the 1 second gust, the 3 second gust, and just on this one, I've actually normalized. That's why it's called a gust equivalent at 10 meters. But this is really what the gust would be in order to satisfy the hub height design ceiling for a class 1 turbine, IEC class 1 turbine. So from a wind loading perspective, a class 1 turbine would be adequate in, but I do want to, it is worth pointing out that it looks like you've got an 18% margin here, like, oh, we're actually well under for, but again, there's a lot of scatter that can all be eaten up by the difference between, Gloria, the synthetic hurricane model, under predicted by 16 miles an hour. This is all wind evaluation, but just to show you that the wind fields are producing something that certainly looks reasonable. And I don't want to get too much into a debate about whether these winds are accurate or are they 50 or the 500, but just to show you, this is the level of detail that went into creating the wave results that I will now share with you from this study. So I want to compare two different sites. So first of all, the Chesapeake Light Tower, that's where the validation you just saw was done with the anemometer on Chesapeake Light, which is a fixed anemometer, so it's not buoy based. It's at 43 meters above sea level, so it's a really good reference anemometer. And we have a wave writer right there. So this is a really good set of validation data. And then Peter, he did several grid points. These were the Army Corps of Engineer grid points, 63197 and 63196. And I'm now going to, so this is the 196 is the one closest to what the time was called the Virginia Offshore Wind Technology Advancement Project, but now is CVOW. So it's not really VOWTAP. I should update the slide. This is the CVOW turbine sites, but it's the same front-end engineering design basis. And then here's the grid point that's nearest to where we have the validation. So the first thing you do in the IEC, when you look at different load cases, extreme loads, you've got the wind speed, the wind hazard curve, and then for every point on this curve, which is 637 different synthetic storms, there's the wave that came with that peak. It's not the time of the peak wave, that's a different curve. This is the peak wind hazard curve. And here it is, and you can see that there's kind of this, even though there's a lot of scatter here, they don't seem to, the waves are not exceeding significant of 6 meters in this water depth. All right, now if we go out deeper to where the CVOW turbines are, again, very similar wind speed hazard curve, but all of a sudden the waves that are associated can grow much larger, up to 9 meters. And this was Swan, and it has all that surfstone breaking. Unfortunately, I didn't think ahead of time because I wasn't aware of this until I looked at the results. Peter did not, there's a flag you can actually set, so you actually record. It's a special flag you have to set in Swan in order to record the percentage of breaking waves. And unfortunately, Peter did not set that flag because we didn't, this is how I guess science and engineering work. We didn't realize we should have said it until we saw these results. I didn't realize, but certainly in the future, you want to really make sure you capture as much as you can as the model is willing to produce the underlying effects. So those are, again, very similar wind hazard curve, not much change in the wind as you go into deeper water, but a big change in the waves. Now we look at the wave hazard curve. So there's the wave hazard curve, and now you pick the peak wave for the same set of storms, and you plot the curve, and then you've got whatever wind happened to be at the time of the peak wave. This is a different design load case for the offshore wind turbines. And again, quite a jump in the curve. There's not much change in the scatter of the winds. I mean, they don't look, they're pretty similar, but boy, again, so again, this is what really first alerted me to there's something going on that our model physics suggest is, and the results, everything you've seen so far is suggesting that surfstone breaking may be important. All right, so now I'm going to go to some observations in the North Sea. These are not hurricane waves, but before, does anyone have any questions kind of about what they're looking at here? And Krish, I know I didn't really bother to, same idea, you've got a log return period on the x-axis, and for the wind hazard curve, that's the wind is on the left axis, and this time in meters per second, and the right it's significant wave height in meters. So any questions about this? These graphs?
No, my earlier comment was in relevance to some members of the audience who may not even be aware of what a return period is. So yeah, if somebody wants to ask fundamental questions, please feel free to do so.
Yeah,
then George can answer them.
Yeah. But remember, from the IEC, it's the 50-year return period that is the driver or the governing for the extreme load design cases, the ultimate limit state.
George, I have a question with relevant to these graphs you're showing, where the wave heights you're showing as being higher in deeper waters, not that deep, but still deeper. Are you getting to the point that these higher heights are because of waves approaching breaking conditions in these
my
depths.
hypothesis for this, and I think it'll be supported. In fact, I actually did the Pheno 1 observation to see if we had any evidence for things, and we turns out we have a couple of pieces of evidence. But yeah, that's what's damping down. It's not the wind. The winds are the same. So the wind, it's not that the winds are creating bigger wave. There's higher wind farther offshore, but it's just in deeper water, the waves can get to a larger height before they break.
Right.
So these are depth limited. We really need a depth limited probability distribution to really sort this out. And again, you see the same thing with the wind, with the wave hazard curve. It's only a 3 meter water depth difference. It's like a 15% difference. Not a huge difference, but there's quite a difference in the SWAN model result.
Thank you.
All right, so let's look at Pheno 1. This is a platform in the North Sea. There was this again, winter storm, extratropical, winds and waves aligned. In the Pheno 1 platform depth is 28 meters, so shallower than the Seabed turbines, which are in 25 meter water depth. And in this particular storm, the maximum wave, I'm going to show, and I wanted to find I have a video link, and I don't know if I can, I'll try to find it and put it in the PDF so that you can actually link and see the video. But you can kind of see, these are still frames from that. This looks a lot more like a plunging or a slamming breaker than a spilling breaker to me, just these two frames. And I'll actually provide the link to that. The significant wave height in this storm, which I also realized I should put on this slide, is 5.4 meters. So the significant wave height is about a little bit more than, it's between 1/5 and 1/6 of the water depth. And you're getting the peak wave height is 0.39 H to D, and you're getting this kind of breaker. When this was measured, this is the kind of breaker you got. So that's it's 1 point, anecdotal, but it's certainly there. Again, there's probably troves of data now at Pheno 1 and elsewhere where we could really, and probably at Block Island if we get the wave measuring devices out there, and likewise at Seabed. So this is really important, I think, to nail down. And that's all I got. It's anecdotal. I admit it. It's not. This is not but it sort of corroborated. Like, okay, you can get depth limitation in much shallower, in much deeper waters. You can get depth limiting conditions in surf breaking. So that's that. And I will, Krish, since I need to wait for the recording link in any case, I will go ahead and be sure to find a video where this can be. I'll put it maybe on my public Dropbox or find a way I can embed the clip in the slides so that people can see it. Because to me, it's pretty dramatic. All right, and then this is really Spencer Hallowell is in the audience. He and Andy Myers and Sanjay Arwade. This really, wasn't even aware of this when I did the original. Everything you see up to now is studies that I did for BOEM. I was not aware of this paper at the time, and it's this one graph kind of says it all. So I'm going to go through this graph, and Spencer, if I make any errors, please correct me. We'll make sure that those get corrected on the final. So these are the different breaking wave criteria, and the Misha criterion is the one that is used for or maybe it's the McGowan. So again, I've got to be careful. I've been mistaken saying it's Mish. It's actually the McGowan criteria, which is the H max over D of 0.78. And what Spencer did, this was a part of, I think, of his PhD work at Northeastern, is he really went back. I mean, there's data, so you can go back and mine this data from 2009. And we're able to find 22 breaking waves during a particular sea state. And so you can see they were rare, but they definitely occurred. And you can see the bending moment at the seabed was, estimated to be 3 to 4 times or 2 to 3 times greater compared to the non-breaking waves, which are the circles. And you can sort of see that they're breaking waves down to H max over D of 0.39, which is this orange line. So again, half the value of the McGowan criterion. So this is really, this is really concerning to me, because I really think that you're going to have these tropical events, and some of these are going to occur. I mean, this is, I can't remember, let's see, the significant wave height, 4.7. That's not a big tropical event. I mean, you know, you really only get, you know, we get those. And so I think the fatigue history is of these in tropical cyclone and hurricane ridden waters of the mid-Atlantic bight. I think they're going to have these high, rare but intense, and they're going to add a lot of fatigue. They're going to eat up a lot of fatigue margin, and I just don't think anybody's really looked at this. And I think that's my story, and I'm sticking to it. Yeah. So we've got plenty of time for a discussion. And Spencer, if you want to come back to this and talk, do you want anything you want to add, or have I adequately interpreted this or synthesized or presented this?
Yeah, I think you have. I really appreciate you bringing this to the forefront. I think my one comment would be the difficulties that we had with the Blythe data are very similar to the difficulties that you had synthesizing the hindcast data, in that at Blythe there was a wave radar taking wave measurements of the sea surface during this time period. But of course, the behavior of breaking waves is that they're very messy in the ocean. And so the wave radar actually could not see that the waves were broken. You kind of had regular wave profiles, and then all of a sudden the sea surface would go flat because it was full of foam and the wave had broken near the structure. So we actually had to use structural measurements to tease out when a breaking wave was occurring. And this similar phenomenon happens when you do these basin models and these hindcasts, is that if you forget, like you said, if you forget that you've turned on your breaking wave effects in your model, your significant wave heights are artificially capped. And if you don't account for that in your 50 or 500 year extrapolation in your extremes, then you're actually going to miss this breaking wave effect because you're below these thresholds,
right.
These depth-based thresholds. And so I think it's very important to keep that in mind. And when we start to, talking about wave design at 50 or 500 year events, whether we consider it a binary effect on whether a wave is breaking or not breaking, or whether we give it a probability distribution, I think that needs to be taken into consideration. It plays a large role in these fixed base forces and moments for design. So yeah, thanks again for presenting all of this. It takes me back a few years. I feel like I'm back.
Well, it's a seminal paper. And one thing I'll also do, Krish, is I'll make sure I put a bibliography in the back. I didn't have time to do that as I've been putting all this together. This is actually the first time this is why I offered this topic, because I just haven't really had a chance to pull all this together in this way. And Spencer, yeah, everything, exactly. I was just like pulling my hair out, like, you're like, well, wait a minute, you've got a depth limited wave height distribution. It's not necessarily, certainly not really, and maybe Forstall and some of these others, so I really think a joint industry project and really maybe something that the Ocean Energy Safety Institute can take on as an early possibility. I think that would really, I just worry that we have, like you said, I worry that we haven't really factored these in. And one thing that we have done is now you can use we hope certainly on both at Block Island, and although funding has not yet been identified for this kind of instrumentation yet, but at both Block Island and Seaval, there are actually forward-looking LiDAR that can actually capture that shape, like you said, that messy, so you can actually see if a wave is breaking, near breaking, spilling, plunging. You really need to capture that face with a LiDAR point cloud, and we really want to do that. And also, Adam Brown, who's now at Gloston in Seattle, he's developed a buoy that can also, it's really interesting, with a very rapid inertial motion unit. He can add much higher cycling. He could actually, there are different signatures for spilling, plunging, and post breaking. So I think, we've got a lot of, there's new instrumentation we can bring to bear that certainly was not available at Blythe. Anything else? This is open for discussion. But this slide is really like, it's just like really should be concerning to people.
I see somebody has put their hand up. So if you can unmute and ask the question, please.
Hey, George, it's Eric Hines.
Eric.
I want to, hey, Krish, how you doing? It's good to see you. Spencer, good to see
likewise.
you.
Yeah, good to see you.
Krish, thank you so much for hosting this today and for opening it up to everyone to join. And George, I want to compliment you on the presentation. It's fantastic. I think you have a narrative approach to talking about this, which is extremely helpful.
Yeah.
And notwithstanding all of your generous qualifications about, whether or not X, Y, or Z is right, I think that what you've put together, which I've quite frankly not seen anywhere else, is an understanding of the problem in a way that, a person sort of seeing this for the first time can get into it and make sense out of it without being thwarted by, mountains of journal articles and all these things. Yeah. And I think you bring this into a way that we could really start talking about this much more widely and with decision makers. And I just love listening to you talk about it. So thank you very much. I think it's a great presentation.
Oh, thank you, Eric. That's really kind of you. And it's, again, I think I credit to Power US because the very first version of this, the earlier slides that showed Hurricane Jose, I remember presenting in Boulder, and I think that's when I first met you, maybe, yeah. So collaboration, not competition, man. We've got to get all the best and brightest together on this.
Well, I think that's right, and I think what the fact that you're at UMass Amherst is particularly poignant because this is really sort of the work that Sanjay Arwadi is doing is at the heart of a lot of the hurricane research happening. And Krish, I know you and Sanjay have been collaborating, and I think that this constellation, getting URI involved, Stefan Greeley and the WAVE guys there, connecting them, George, with the work that you're doing, and linking this all together with the extreme events is kind of, that was always the dream of Power US, all the way back to 2015, 16. And I just think that we should continue to pursue that. When you have a team that's that big, you've got to, you can't go after small pots of money. But I do think the community is forming. And I guess what's exciting about this to me is that I see the momentum and it just all feels very real. It feels like we're getting closer to putting together the team that can figure this stuff out.
Thanks, Eric. Yeah, I hope so. That's really, and again, so Krish, anyone, however you want to distribute this is all public domain, everything funded by by federal or state tax, public monies. And I'll just say at the end there's a lot more detail in this report, 2014. So it's now 7 years out of date, but I still think some of the concepts introduced in this report might be useful. And we definitely, we are in a hurricane prone ocean here that they don't experience in Europe. So.
Hey, George, for the benefit of some of the students in the audience, can you elaborate on why breaking waves are a problem for offshore wind turbines, and what does it actually mean when you have higher waves than what you designed for? What does it do to the system, offshore wind turbine system itself? Thank you.
So good question. So it's not so much the height of the wave, because the height of the wave is limited, but it's the nature of the wave. So a near breaking wave, a spilling breaking wave, those waves, you can use Morrison equation. It has a drag component and an inertia component, well understood, and it's at the heart of most of the structural design codes for the offshore oil and gas platforms in the Gulf of Mexico. If you really get down to the base, they're very sophisticated, but at the end of the day, you've got a drag load that's due to the water particle velocity beneath the wave, and then you've got the inertia load that's due to the acceleration beneath the wave, and those in a linear airy wave, they occur out of phase with each other. But anyway, as you get steeper and steeper waves, there are all kinds of ways to use the Morrison equation. But the loading of a breaking wave, it creates an impact load that traps a pocket. There's a pocket of air, and it creates a much. That's why these overturning moments are higher. There's actually a great paper, and it's Dolan is the senior author, and again I'll put it in the bibliography. Jim Dolan at MMI did a joint industry project, and they looked at the loads on a jacket and a monopile at a hypothetical site using the 5 megawatt turbine and this 25-meter water depth. It was actually off Massachusetts. And again, I'll be sure I put those 2 reports in the bibliography. And you can see that there's a step change in the load, the total load. You look at the wind thrust load, you look at the wind drag on the tower, you look at all these loads, and when you've got a breaking wave, it just dominates everything. It dominates the entire load profile experienced by the turbine. So it has and of course its main impacts are going to be on everything loaded that's holding up the nacelle, the substructure. There's actually going to be an impact probably on the pile or the suction bucket that's got the connection to the seabed, because that slamming load that again Spencer was able to detect, just by looking. You can see the kind of ring. There's a kind of a ringing effect when the wave hits, and that's how you know that's a structural way to. There are a lot of ways you can really confirm that now, especially if we get some approaching wave measurements with LiDAR, and we've got some sophisticated wave radars. I mean, I really think we can solve this problem, but what it's really gonna do. And Eric, now this is your wheelhouse, not mine. But correct me if I'm wrong, but I believe that at the end of the day, these substructures are going to be dominated by fatigue and not ultimate limit state. Is that a fair generalization?
I think that's a fair generalization. I think it is, but I think that the community is also working on that question, trying to understand what the relationship is. And I was wondering, George and Krish, if what you thought of, like, I think of a breaking wave as kind of like if a normal wave is like you're pushing on the turbine, a breaking wave is like you're hitting it with a hammer.
Yeah, exactly. And it's pushing and hitting with a hammer at the same time. So
yeah, that's right. In fact,
George talked about the Morrison equation. When I have worked with the breaking wave loads on offshore oil and gas platforms, and in particular like concrete gravity platforms, 2 things that are interesting there is when the breaking wave or when a steep wave approaches a structure, the presence of the structure steepens the wave a bit more, causing it to break at the location of the structure itself. So this is in a way, the structure kind of induces the wave to steepen a bit more and break at the location. So that's one interesting thing. And the second thing is you can modify Morrison's equation, as some of you have worked with it now. You can modify the Morrison's equation to add a slap term, which is basically just like you said, a hammer, like a hammer force. It's like a slamming term. So you add a third term to the Morrison's equation. So you have inertia, drag, and a slam term, which together kind of gives a reasonable, but it's still very empirical, just like the rest of Morrison's equations.
Yeah, one of the things, again, I want to make sure I include those MMI reports, because they actually break down. There's the drag inertia component and then the slam component. And again, you can just see how that slam component is so critical. And I just, I think trying to sort out what, I certainly know, I don't know if this is true of well, I know I can say now, because we had this workshop at the IPF in Richmond, that one of the things we've talked about, if you put a little bit more steel in the monopiles, could you get a 35 or 50-year life? And the answer is yes, but the industry is not doing that. The industry says we want to get as much steel out of the monopile as possible. And so now the question is you know, what kind of how much margin do you really have to erode erode in a design sense? How much margin do you have really to play with? And if you're not factoring in these, you know, these events that are likely to occur in June, July, August, September, October, I mean, a big part of the year, you might have a half dozen episodes where you might have within a system. We just don't know. I mean, we've just got to really look at it. So and it hasn't, I just don't think anyone's looked at the fatigue, the effect on the fatigue, and how much of the design margin might actually vanish if you factor in braking versus non-braking waves as you build the rainfall of the fatigue history.
Yeah, that's a very good point, John. Thank you. Sorry.
I agree. And, you know, I think another thing is when you think about the North Sea, everybody's known that these turbines that they're installing, a lot of the turbines in the North Sea are 3.6s and smaller. And everybody's known they were growing. And when you think about the United States, you know, we may install a couple of 8s here and there, but mostly it's 12 and larger. And I think that we have a completely different problem on our hands than anybody in the North Sea ever dealt with, which is we're not going to want to tear down a 12 megawatt turbine, even if we want to replace it with a 20 megawatt turbine. Like, we'd have to space them further apart. Like, these things need to be built to last. And I think that the question of fatigue is becoming more and more of a question. And I think that Europe has really only dug into this anew in, let's say, the last 5 or 10 years. So I kind of feel like in many ways, this is a cutting edge conversation. And when you couple it with the fact of breaking waves and the fact that we have storms that North Sea doesn't have, it all makes sense that these remain areas for exploration.
Yeah. Excellent point.
Spencer, do you have any more comments, Spencer? Again, I really think that this is such a, and I've actually seen this other author. I mean, this is a really important result. I mean, you know, I know now you're at Maine and you're probably more focused on floating because of your location at the University of Maine. But what are your thoughts? I mean, any more thoughts or ideas? I mean, like if you know, now that this has kind of brought back some memories and some of your own thinking on this, and I really appreciate that you took the time to attend today. Do you have any closing thoughts for us? We've got 5 more minutes.
Just, I guess one quick thought is you've spoken a lot about hurricanes, but I think, you know, especially as you start traveling north up the coast, winter storms and extratropical storms start becoming a serious consideration. They may not pack the more extreme punch in terms of wind speeds that a hurricane off the coast of Virginia or North Carolina might, but those extratropical storms move a lot slower than hurricanes do, and they have a lot larger radius to their maximum winds than a hurricane does, and so you can have a much more developed sea state. And we don't have as many synthetic extratropical storm catalogs as we do hurricane catalogs. I think that's one potential gap in the understanding of the risk profile of these turbines is, you know, what's a 50-year winter storm look like? What does a 500-year winter storm look like? And then just kind of a closing thought, I think, you know, trying to combine these extreme wind wave effects and then this kind of binary consideration of a very large extreme force. When you're talking about statistical distributions of winds and waves and all of those things, it becomes a really technical and difficult thing to make a decision on when you're looking at the design of your system. And that's just for ultimate limit state design. Like you said, if you now start considering this in fatigue, I think it becomes a very difficult design problem. And I think, you know, we want to keep things conservative, but we want things to be really realistic. In order to capture the realism, we need to make sure that when we run these models, that we're just not blindly taking the outputs from the models. We need to really understand what the physics are behind them, and that we don't miss something that can cause a 2 to 3 times larger force effect on the structure that we're designing. So yeah, it was a really difficult problem to work with when I was doing my graduate school research, and we still run into these design issues. There's a lot of philosophy that goes into it. So so thank you.
Well said. Thank you.
Well said. Yes.
All right.
Let's see if rest of the audience, anyone has any quick questions we can answer.
Well, thank you again, Krish. I really, this was really great. I'm again so appreciative that that Eric and Spencer are here, and I know Lou, representing, you know, has been concerned about this because of the Avangrid Renewables Kitty Hawk project, where the hurricane exposure is greater. So, if there are no more questions, thank you, Jen, for setting this up and recording.